All right, guys, we'll get started. So, thank you very much for joining us today. This is the first part in our three-part webinar series on simulation productivity. And what we're going to be doing in this three-part series is talking about basically underused tools in simulation. A lot of the time we talk about simulation, we spend time focusing on analysis capabilities, basically failure modes, whether it be material yield failures or buckling failures, thermal analysis, geometric optimization, basically just the features. What we're going to be doing in this series is taking basically 3 different webinars over the next 3 weeks and talking about not necessarily how to do more with your simulation, but how to do what you're doing now faster than you've been able to before. So specifically, this webinar is going to be on contact and how to save huge amounts of time with the new contact tools in SOLIDWORKS Simulation. Because every simulation that involves multiple parts does involve contact, and troubleshooting that can be one of the toughest, well, not necessarily toughest, but most time-consuming and frustrating parts of any simulation analysis. So what we're going to do today, guys, we're going to start with an overview of contact and just a reintroduction to those of you that may not have used contact in a while or haven't used analysis before. Then we'll talk about how to apply contact and then the new contact tools in SOLIDWORKS Simulation. And these tools have came out in the last couple of years and they haven't been really highly publicized yet. So I think you guys will enjoy them, and I know this is going to save everybody a lot of time. So let's get started. What is contact? To start with? Well, when we're analyzing one body in a simulation, we never need to worry about contact. If we just have one part, we just need to go in, tell SOLIDWORKS how that model is restrained, and then how we're going to load the model as well, and then click Run. So we'll basically see how that load gets transferred, how that model deforms, what the stress is like, etc. But when we have more than one body, we need to define how they interact with each other. There's really 3 ways we can do this, and it actually boils down to really 2 ways. So there's 3 types of contact in SOLIDWORKS Simulation. There's bonded contact, there's allow penetration contact, and there's no penetration contact. And I'm going to start by saying allow penetration is basically just a way to tell SOLIDWORKS to ignore contact between 2 parts. So it's really not a contact condition, it's more of a contact exclusion. So that leaves us with 2 main areas. We can either have parts that are bonded or no penetration. So what happens when parts are bonded? If we have part A and part B, and they're bonded together, well, what happens actually at the interface where those 2 parts touch, SOLIDWORKS actually bonds the nodes together. And doesn't even bond it, it merges the nodes. So the node from part A and the node from part B that lay on top of each other are actually merged into one single node that's connected to elements on both parts. So it's not like a weld that's just around the perimeter. It actually joins the entire touching surfaces of the parts. So now if they were the same material, it would be more like part A and part B are machined out of one block of material. Now, that's actually the default contact condition in SOLIDWORKS. Unless you specify otherwise, everything's going to be bonded. But some things don't behave that way. Sometimes we need realistic contact. We need things to be able to press on each other, slide a little bit, basically develop a contact patch, and have parts start reacting off each other. That's where no penetration contact comes in. And when we set no penetration contact, some people refer to this as realistic contact. It does basically make the 2 parts not penetrate each other. So when part A comes into contact with part B, it actually starts basically developing a contact patch there and transferring load between the 2 parts and deforming both parts as that happens. Now, those are the 3 contact conditions we have, but we also need to talk about something called the contact hierarchy, and that's how we apply contact, because there's 3 basic ways. We can apply contact globally, or at the component level between parts, or contact sets, which is local contact between faces and edges. And the neat thing is here, if you use this contact hierarchy correctly, it can save you a lot of time. So to start with, there's global contact, and you'll see in SOLIDWORKS, I'm just going to quickly switch over my SOLIDWORKS window here. Anytime you see a multi-body study in here, you're going to see this component contacts folder. And it's going to tell you the global contact is bonded there. So what that means is any touching faces are bonded. Now, I will say that does only apply to initially touching faces. If 2 parts are separated, even if it's a manufacturing clearance of a few thou, that global bonding will not work. So we'll talk about that in a second. But the main scheme here is to use your global contact to basically set the contact condition that will affect most of your parts. So if most of your parts are bonded, set your global contact to bonded. Then we can go into the other components that are no penetration, and we can use component contact or contact sets to set those. And you'll see here, component contact actually overrides global contact. So even if global is set to bonded, if you have two parts set to no penetration with component contact, that will override your global bonding. And contact sets will override everything. So when you get down to the face level, and basically the more specific you get, the more precedence that takes. So I can have everything set to bonded, component contact set to bonded, and if I go into my contact set and say these two faces are no penetration, that will take priority. Now, so again, global contact for your most common condition, and then set component and local contact as needed to specify the other contact. Now, global and component contacts only apply to the initial touching areas, as I just mentioned. So if you have some separation in there, manufacturing gaps, gasket spacing, etc., or if you have two parts that start separated and will come into contact during the analysis, you'll need to set that contact manually. So what can go wrong with setting up this contact, and how do we apply what I was just talking about? Well, let's have a quick look. So we're going to have a look at these pliers right here. And one of the quickest ways to find out what's going to be bonded with this global bonded contact is to run a very quick interference detection. So I'm just going to pop to my Evaluate tab and say Interference Detection, and I'll calculate it. Now, it's going to come up and say no interferences, but I've got a neat option here I can turn on, which is Treat Coincidence as Interference. So this will show me all touching faces. There we go. I can very quickly see where my three parts are connected. My two arms and my pin. There's contact there, 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 etc. So anywhere those parts are touching, the global bonded contact is going to bond them together. So if I wanted these pliers to behave realistically, but I just left the contact like it is right now, what would happen when I run it? So what I'll do, I'll just remesh this quickly. And this was an older model, so I just have to remesh before I run. And I'm just going to do this as a draft quality to just keep it nice and fast. So when I run something that's bonded, I may get some very unintended results. In this case, I see, at first glance, yeah, the pliers are bending like I think they would, but if I look closer, I have no deformation and no stress happening in the jaws of the plier. It actually all stops right at the pin right here. And that's because of the bonding. It's gone in here, and it's actually bonded the two jaws together and the pin anywhere that contact. So really, we don't have pliers here. We have a plier-shaped object that's been sort of CNC machined out of one block of metal. Now, I can fix that really quickly in this case by just going into my contact definition, and I'm going to say instead of bonded, let's make everything no penetration. Now, when I do that, it's going to ask me to remesh because it has to go in and unbond all those bonded nodes. So we'll just mesh and run this one more time. And now if I animate this, we'll see it actually behaves like I would expect. I see the arms moving, but I also see the jaws deforming in here, and I can see relative movement between my two plier arms. So things are rotating, things are sliding, that's working correctly. But what if we had some gaps in there? Well, if I had a gap between my two arms, say between this face and this face right here, even if it was just a small manufacturing tolerance of a couple thou, I'd have to use a contact set to set that. And the way I do that is to go into my connections folder here, and this is where I can do component contact, which is just between parts, or contact sets. So I'm going to do a contact set, no penetration between this face and this face right over here, and that will override any other contact that I have in the model. So in this case, the no penetration global took care of everything, but that's how I would set contact sets. Now, move on to the next question. So that was, again, a very simple example that we just looked at with those pliers. And with that, we could easily go in by using things like interference detection and that treat coincident coincident bodies as interfering. We can see what's touching what. But what if we get into more complex models? What if we have 10 plus components or 50 plus components that have contact between them? Like these two examples, a little roller rocker here and a chain over on the right-hand side. Well, these can be much harder to troubleshoot when you get into many contact sets. So Now, what we'll do, we'll talk about why that's a problem, and then I'll show you guys how to fix it. So troubleshooting contact can be three things. It can be time-consuming, can be frustrating, and it's really not a productive use of your time. When you're sitting there spending half an hour or an hour going through and troubleshooting your model, it's time you're not making design decisions. So how do we fix that, guys? Well, first thing we're going to look at today is the contact visualization plot. Now, this has been around for a couple of years. It was actually introduced in 2014, but it hasn't been highly publicized yet. We've run a couple blog posts on it, but it's something most people don't really know exists. Now, this is available in both of our higher-end simulation packages, the Simulation Professional and Simulation Premium, and it's a really nice way to graphically view your contact. So, not just what faces are touching, but what contact condition is set between them. So, how do we get there? Well, it's really easy to use. All we do is we right-click or use the right mouse button on our connections folder or any contact definition, and we're going to start a contact visualization plot. Now, when we do that, we can select the whole assembly or specific parts, and then we can calculate that. Now, it's going to go in and color code our contact to this color list you see on the right. So anything bonded is going to show red, no penetration is going to show purple, but we also handle other contact sets. If we get into thermal analysis, we can show basically contact resistances or insulation. We also support the shrink fit and virtual wall conditions here. So just about any contact we want, we can visualize. So let's see some examples of that. I'm going to jump back into SOLIDWORKS here, and I'm going to start with that little rocker example that I had. So if we have a part like this, or an assembly like this, we've got a handful of components in here, but there's a lot of touching faces here. So how would we set this up? Well, let me pop into my simulation study, and I've got one set up already. Just got a couple fixtures and some loads applied here. But look at our contact folder. If I go into my component contact, well, the global is bonded, but my contacts, well, I've got multiple ones in here. So if I needed to troubleshoot this, it might be a manual process of going through and saying, what's in this contact set, what's it set to, what's in this one, what's it set to, etc. But now, contact visualization plots. So you can right-click anywhere on your contact sets or your connections folder and say, start a contact visualization. Now, what we'll do here, I'm going to click the calculate button, and by default, it's selecting the entire assembly. And this is what we see. So very quickly, it's going to tell us exactly what is set to no penetration and what is set to bonded between all of my components. So I can very quickly visualize where that contact is applied, and I can also get more information. If I want to look at individual contact sets, I can do that. I can say for this bonded contact in here, what are the two parts? Well, that's between my outer piece right here and that tube that runs through the middle of it. What if we go down to this one over here? Well, if I zoom in on that one, that's between this inside little wheel in here and the outside plate. So with that, you can run through and visualize all of your contact very, very quickly. Now, we'll look at a couple other examples here too. Let me open up a quick chain example. So I'm going to take a quick look at this chain right here, and I'm just going to pop back to one of my full chain links. So we're looking at a roller chain here, guys, and there's a lot of parts inside this. If I do a quick section on this, you're going to see all the touching faces that we have between the pins, the bushings, the inner links, the outer links, etc. Every single face in there is going to need some sort of contact defined on it. So how would we go in and do that? Well, this is where contact visualization comes in. Again, if I can go in and apply these manually, but if I want to check, I can very quickly go into my contact visualization plot and see what's bonded to what in here. Which faces are bonded, which are no penetration, etc. Really helps me visualize what those contact conditions are, and of course, if I can see them, I can very quickly fix them. So while we're here, guys, I'm going to take a quick aside on contact sets. I'm going to talk about automatically adding contact sets, and I'll show you what I mean. Well, I say automatic. It's not really automatic, but it's a much quicker way than doing it manually in sets like this. So in a set like this, what I might start with initially is doing an exploded view, so I can actually visualize all those contact faces, and then I'd start my contact set window. And I could go in here, I could apply contact to any of the faces that I need to. So for example, if I need to, let's say, do a no penetration contact between this bushing and this roller, go and say no penetration between this face and these faces, apply friction, anything else I need in there, and OK. And then I could go in and do it for the next bushing. And then I could do it for the next base, etc. You see where I'm going? It's not a very fast way to do this. So I'm going to delete that contact set. And I'll show you a little bit quicker way when you're dealing with multiple sets like this. What we can do, we can go into our contact sets and we can use the automatically find contact sets option. So this will let us find, by default, any touching faces, or you can set a threshold, gap limit, to find faces that are within a certain distance of each other. So if I say find me all of my contact sets for touching faces here, you're going to see what happens. It very quickly goes down and shows me there's 25 different contact sets in here. And it's going to highlight them. So there's these. I've got my initial pin being bonded to the outside or the inside face of the link there. So I can actually set these right here. No penetration, bonded, etc. I could say, well, this is going to be bonded. Click the little add button, create contact sets. That one gets added and it's removed from this list. So it's only showing me ones I need to see now. This one could be bonded as well. And the neat thing here, you can actually do multiple ones. If I know I have multiple no penetration faces, like let's say we go into these two in here, I need to set that these are, let's say these are bonded together. I can select both of them or even all of the sets I need from this list and say both of those or all of those are bonded. Now, the rest of them, maybe the rest of them are going to be no penetration. So go down and say no penetration, add those, and maybe these last two. I'm not actually going through these in detail, guys, just an example. Bonded. So very quickly, I've gone in and created a huge amount of contact sets without needing to do each one individually. So with that tool and your contact visualization plot, you're going to be able to apply contact much more quickly and also basically visualize and make sure that contact is what you want and what you're expecting out of the analysis. So it's going to save you guys a lot of time and frustration in your analysis. It lets you see that contact clearly, lets you quickly find and fix your contact errors, and the ultimate goal here, guys, you want to get to accurate solutions faster without any unexpected surprises or making a design decision and then going back later and going, oh, wait a second, were those two faces bonded when they should have been sliding, etc. So hope you guys like that, and I encourage you guys to try that tool out. And if you have any questions, I'll have my contact info at the end. Feel free to give me a call. I'd be happy to walk through some of this with you or show you some more tips and tricks. So the next thing we're going to talk about today is unstable models, and we're going to talk about how to fix this with a brand new tool in SOLIDWORKS 2015. So how many times have you guys seen this message before? Model is unstable. You think you're set up right, you think you're correct, and you run it, you get that message. And it actually depends on the solver you're using. If you're using the direct sparse solver, you're going to see that model is unstable message. And it says right here, check that you have adequate fixtures applied to stabilize the model. But if you're using our iterative solver, the FFE plus solver, you're going to see something a little bit different, which is this message down here. The iterative solver has stopped. The solver has numerical difficulties. Model may not have adequate fixtures. So most people that run simulation have seen one or both of these messages many, many times. And you go, what happened? Now, the root cause here, if you forgot to apply any fixtures to your model, let's say you just had a simple beam with a load on the end, but you forgot to fix the other end, you'd see this model, because basically that part can move around with rigid body motion instead of deforming. Now, the other thing that can cause this is incorrect bonding. Your global fixtures might be fine. You might have a good path to ground for most of your loads, but if you have one part or a couple parts that aren't bonded correctly, either you forgot to bond it or it's set to no penetration instead of bonded, then you can also see instability. And it may not be every part, just one little part in the analysis. So, yeah, what does that mean? We just talked about that. It's either missing fixtures or it's missing contact. And both of those lead to basically either one part or the whole model being able to translate and rotate in a rigid body mode. So we're going to talk about how to fix those today. The old way was looking through all of my fixtures, looking through all of my contact and then doing some critical thinking, going, what could move? How could it move? Am I sure it's correct? There's also some tricks you can use with inertial relief in there to try and show what's not bonded, but this is a very time-consuming process. It's never fast, and again, it depends on the complexity of the model. If you've got 4 parts, it's going to be pretty quick. If you have 60 parts and 60 contact sets, well, it's going to be much, much, much longer. Well, that was the old way to fix it. What's the new way? Well, we just talked about contact visualization plot. It's a great way to see what's bonded and what's not, but the new tool is find under constrained bodies. And this is brand new this year, guys. Just like the contact visualization plot, it's available in both our Simulation Professional and our Simulation Premium packages, and it's going to save everybody here a ton of time. So how do we get in there? Well, just like we got into the contact visualization, we're going to right-click on our connections or our contact folder, and we'll go to the Find Under Constrained Bodies. So let's see what this actually does, guys. I'm going to pop over here, and we're going to find a quick model. So this is a pretty simplistic model here. I've just got a base plate. I've got a tube running up the center. I've got a piece of structural steel, and I've got a plate mounted on top of it. Now, I'd like to set up a quick study here. So I've got some material applied. We have alloy steel applied to everything. I'm going to do something really quick. We're going to fix the bottom. So we'll fix that. Then we're going to apply a load to the top. So I go in, I'll apply a force here, and maybe we'll say that's a 1,000 Newton force, something like that. Okay, looks good. Let's mesh it. So I'll create my mesh. I'm just going to check which solver I'm using here. We'll use the direct sparse. Now I'll run it. And of course, we see that message. Model is unstable. So, what can we do? Well, I could use that contact visualization plot and quickly visualize this, but I've already showed you guys that. I'm going to jump right into the Find Under Constrained Bodies. So if I right mouse click on my connections or my contacts, there it is right there, Find Under Constrained Bodies. So this is a very simple tool. There's no inputs here. All we do is click the Calculate button. And what it does, it actually runs a very, very quick simulation on this, just to find out basically what things can move and how they can move. So let's have a look. If I click Calculate, it's going to take a second. It instantly starts the solver, and then it's going to come down here and tell me I have some under constrained bodies. So what are my bodies? Well, group 1. So it's actually my top 2 bodies here. Those are bonded together, and they act as a group, and it shows me how these can move down on the bottom. So 3 translations. Well, when I click on that, it actually shows me the body, or in this case, bodies, can slide in that direction. They can slide in this direction. And finally, they can slide in that direction as well. So all 3 translational modes are unrestrained there. Now, what's causing that? Well, it's probably because I forgot to bond those 2 pieces, or if I'm just, in this case, I'm just using global bonded contact, it likely means they're not touching. So if I go up here and look, well, yes, I actually have a small gap in here. This might be for a gasket or for a weld clearance, something like that. So that's the issue, and we've very, very quickly found out basically what that causes. That causes rigid body motion of the upper 2 parts that aren't connected down to the fixture. So how could we fix that? Well, a couple ways. I could go in and bond those faces, or I've got an even quicker way using my global bonded contact. And then this, again, new in 2016. If I edit my global bonded contact, I can go in here and say we can do global bonded even for non-touching faces. So I know those 2 faces are actually only, they're less than 0.1 inches apart. It's like 0.05. So if I go down here and say take any non-touching faces that are within a threshold, I'm going to say 0.1 inches here, bond them. So just by turning that option on, clicking OK, we'll mesh and run this one again. We'll see that solves our problem completely. I can now go in, I can see how this behaves. I'm deforming the entire model, and we're fixed. Now, the one final thing I'll show you guys, if I run that Find Under Constrained Bodies again, what happens when your model is constrained correctly, like this? Well, you're going to see a message like this come up. Model is fully constrained. And that's a good thing. You can be confident that it's definitely not the constraints causing the problem in your analysis. So that's a very simple example with just one piece that was unconstrained. Let's look at something a little bit more complex. And we'll look at this model right here. If you guys came out for the What's New in 2016 sessions, you may have seen some of this already. But what we have here is a large tower, and everything in here has been done with shell elements. This is all just surface modeling. But if I go to run this right now, I'm going to find the exact same problem I had before, which was the model is unstable. So let's go in and do a find under constrained bodies on this one. So I can do a find under constrained bodies. And this one's going to be kind of a worst case example. So it actually shows us here almost all of the bodies. I'll just mouse up through that list. Almost all of the bodies have multiple modes of translation. So let's see what that means. Well, what's body 1? Let me click on body 1. Put in this beam right up here. Well, this has 3 translations and 3 rotations involved. So it can translate in this direction, this direction, and this direction. And it can also rotate around all 3 of those axes. And it's going to show me that. It can rotate this way. It can rotate this way. And finally, it can rotate this way in the model. And that's pretty common for all of my bodies in here. I'm going to see 3 translations and 3 rotations in there. So this works not just for single sets, but even if you have just about every single body in your analysis, and you might have 30 to 40 bodies that are all unconstrained, it's going to find all of them for you. And this is another neat case where I could go in and use that new global bonded for non-touching faces, because that's the issue with all of these. If I zoom in really tight on these models, I'll see some air gaps in here, and those air gaps are what's preventing the bonding from happening. So again, if I went in just into my global bonded contact here, and I quickly use the non-touching faces option, say let's bond everything within 2 millimeters of each other, that's going to fix my problem. So I'll mesh and run this one more time. And this time, it works. So we've gone in there. We found we had basically like 30-something unconstrained bodies in there. With the new tools, we could quickly see what those bodies were and then go into our contact condition and add contact between those non-touching faces, and we've troubleshooted that. So that would have taken much, much longer to do last year before we had these tools. And to be honest, guys, I think this Find Under Constrained Bodies tool is one of the nicest additions we've had to simulation in the last 5 years. Or so, and I hope you guys agree with that. Now we'll go back to the screen. This Find Under Constrained Bodies tool lets you quickly find out which bodies are causing you problems, how those bodies are under constrained, so translational or rotational modes, and finally being able to quickly fix any issues caused by gaps in the bonding with the new bonding options. So, in review, guys, we showed 2 great new tools today that have one that came out in 2014 and a couple that came out in 2016. So, the contact visualization plot lets you very quickly see all of those contact conditions. Again, if you can visualize it, you get a better understanding of it. And then the second thing, we can actually find out any bodies that are unconstrained and not basically not bonded or not restrained properly in the analysis. So with those 2 tools, guys, I think it's going to speed up just about every assembly analysis that you do. So thanks very much for your time. My contact info is up there in the top right corner. Guys, if you have any questions and you'd like to contact me directly, feel free to contact me at my email address there. It's just peter.chalboden@javelin-tech.com. Or you can dial into any of our Javelin numbers Canada-wide, and you can reach me at extension 270. I'm the Simulation Product Manager for Javelin, and I'm happy to talk about anything simulation related, not just FEA, but CFD tools, our plastic tools, sustainability, etc. So thanks again, guys, and I hope this has been a productive session for you.